Okay, here we go. 4.1, basic fractions and equivalent rational expressions. So some of this kind of goes back to junior high stuff, just on when we're talking about fractions. And then, of course, we'll have to figure out what is a rational expression and then what makes those equivalent. Well, let's just start off. We have 4 over 14. We want to reduce the following fractions to lowest terms. We're looking for a number that goes into both 4 and 14, which is going to be 2. And so the way we're going to do it, actually, let's show a little more work here. Where's my eraser? So we'll say, well, we can divide 4 by 2, and we can divide the 14 by 2. 4 divided by 2 is 2. 14 divided by 2 is 7. And so the lowest term, 4 out of 14, in the lowest terms, is 2 out of 7. 21 out of 45, so what goes into both of those? So we don't necessarily have to get there in one step. I'm going to start with, we'll divide both top and bottom by 3, so that gives 7 over 15. And then what we're going to do is look, is there a number that goes into 7 and 15? And the answer is no, so that's it. This one. So we can divide by 2, which would give us 21 over 12. Then we can say, wait a sec, that divides by 3, which would give us 7, and 12 divided by 3 is 4. So to go there in one step, we could have recognized that both of those were divisible by 6. 42 divided by 6 is 7, 24 divided by 6 is 4. So what's important is just that we end up with 7 over 4. It doesn't matter if we have an intermediate step there, right? So lowest terms means that when you've got this fraction, there's nothing that goes into both of these. Okay, there's no common factor. Whereas here, not lowest terms, because both of these are divisible by 3. Evaluate. So evaluate means come up with a value. So if we're going to add or subtract fractions, we need a common denominator, right? And so the lowest common denominator, so we're looking for a number that both 8 and 2 go into. So 2 does go into 8. So our lowest common denominator is 8ths. So we're going to want to change the half. So instead of 1 over 2, we're going to want this 1/2 to be something over 8. So the way we do that is we're going to multiply. And we're going to say, well, in order to make the 2 into an 8, I have to multiply it by 4. But if I just multiply 2 by 4 and get 8, then I've changed this value. It's no longer a half. I can't write this as 1 over 8. That's not equivalent. So to be equivalent, I have to multiply by a fraction that's actually equal to 1. 4 over 4 is just 1. And when we multiply a half by 1, we're going to get still 1/2, but it's going to be in a different form. So that's 3 over 8. 1 times 4 is 4. So remember when we multiply fractions, we multiply numerators, multiply denominators. So 1 over 2 is equivalent to 4 over 8. And 3 over 8 plus 4 over 8. Okay, now we've got a common denominator. That'll be 3 plus 4 over 8, or 7 over 8. Where am I going to squeeze this guy? So 4/5 minus 3/4 are, I'm just going to come up here, we'll start here, our lowest common denominator. So basically I usually start with the larger number, 5. Does 4 go into 5? No. Okay, how about 10? Next one up is 10. Does 4 go into 10? No. 15? No. 20? Yes. So to make 4 over 5 into something over 20, I'm going to have to multiply 5 times 4, which means this has to be 4 over 4. It has to be an expression that's equal to 1. Minus 3 over 4. Now to make this 4 into a 20, I'm going to multiply by 5. So if I put 5 in the denominator, I need 5 in the numerator, right? So again, this is just 1. 5 over 5 is 1. 4 over 4 is 1. This gives me 16 over 20. Minus, and this is 15 over 20, and that's equal to 1 over 20. I don't necessarily need to combine them like this. I can just do that once we have the common denominator. 15 and 12. Now you could go 15 times 12, which is 180. Okay, and then use that as a lowest common denominator, but it wouldn't be the lowest, it would be a common denominator. So, oops, moved too far. What I like to do is take multiples of 15. So 15, does 12 go into 15? No. Okay, what's next? 30. Does 12 go into 30? No. Okay, what's next? 45. Does 12 go into 45? No. What's next? 60. Does 12 go into 60? Yes. So our lowest common denominator is 60. So that'll be 4 over 15. So to turn a 15 into a 60, I'm going to multiply by 4. Whatever I do to the bottom, I do to the top. So multiply it by 4 as well. 5 over 12. To turn 12 into 60, I multiply by 5. Whatever I do to the denominator, I do to the numerator. Multiply that by 5 as well. This gives me 16 over 60 minus 25 over 60, which will be equal to 2 minus 16, negative 9 over 60. Okay, but that reduces, right? Because 3 goes into 9 and 3, so that becomes negative 3 over 20. Okay, so the final step is to reduce. Now, we couldn't have gone with 20s here anyways, right? Like, that wasn't going to work. We could not go with a 20. And neither of these could actually reduce 4 over 15, right? But by going to 60 and then combining them, we end up with an expression which, although it's over 60, is not the simplest form, right? So remember, we want simplest form. And the simplest form is just to say, oh, we've got a reduced fraction. All right, let's practice. We've got some multiplying and dividing. So when you multiply, let's do this the easy way. There is some canceling that could go on, but the easy way is just to say, multiply the numerators, right? So it's 1 times 2. Multiply the denominators, 4 times 3. 1 times 2 is 2. 4 times 3 is 12. 2 over 12 reduces to 1 over 6. Okay, and I'll show you a way to do that, how to do that on your calculator. We'll do that in a sec. So let's do this guy next. I think I need a toolbar. So again, there is some cancel. You could cancel 5 with 15, 4 with 6. I find that really, it's unnecessary. And because this time we're actually going to use our calculator to simplify this. So on the top we've got 20, and on the bottom, okay, let's just turn this on. We have 15 times 6. That is not a 15. 15 times 6, which is 90. So 20 over 90, okay, I don't think we need a calculator to do this, right? Both divisible by 10 is 2 over 9. Okay, but you know what? We can do it. So if you go 20 divided by 90, now if we do that, we'll just get a decimal, right? 0.22222. So what I usually do is I go 20 divided by 90, hit the math key. And you notice the number 1. So in math, the number 1 thing is fraction, 2 fraction. You see the little arrow? We hit that. So that says divide 20 by 90 and convert it to a fraction. And boom, we get 2 over 9. So depending on your calculator, you may see it as 2 over 9. You may see it written as, 2/9. Depends on, if you have an 84 or an 83. It doesn't really matter either way. Okay, 3 over 10 divided by 4. So we can't actually divide. You can't divide a fraction, right? Instead, what we do is we change this to a multiply. And we multiply by the reciprocal, right? Some people call it kiss and flip, right? Like there's your kiss, like X's and O's, X, X, X. There's your kiss, and then flip. You flip that over. There could be some reduction. No point, right? Don't bother. We got calculators. We can do this. And the thing with doing reductions and canceling is sometimes you lose what's going on there. So we've got 3 times 45, which is 135. 10 times 4 is 40. So I'm going to say divided by 40. Now see, when I say divided, it says A and S. That's just answer. It just brings that number back down. Hit math. I always call it like math enter, enter. Because you hit math, you hit enter, you get the 2 fraction. You hit enter again, and you get the reduced form. Right, which is, lowest. Now I'm finding the eraser when I don't want it. Lowest, which is 27 over 8. Okay, let's disappear that for a sec. All right, that's basic fraction stuff, right? I mean, this is elementary, junior high stuff. So rational expressions, which really that's the whole unit, right? Rational expressions. So what is a rational expression? It is a fraction that has a polynomial. Okay, so polynomials are expressions, right? Like polynomial could be x squared plus 2x plus 7. Polynomial could be x plus 15. Polynomial, as a matter of fact, could just be a number. It could just be 10. So it's a fraction that has a polynomial for both the numerator and the denominator. Okay, so even though 10 is just a number, that is considered a polynomial. And then x plus 15, that's a binomial. It's got two terms, right? It's got a variable, x plus 15. Okay, so this is just an example of a rational expression. Some people call it an algebraic fraction, okay? Because now there's some algebra here, right? Like x plus 15. But it's always a fraction. Equivalent rational expressions. So why do we want those? Well, up here we needed equivalent rational expressions, right? We needed equivalent. Notice they both had to have an 8 in the denominator, right? You need that common denominator. And in order to do that, we need an equivalent rational expression. So 4 over 8 is equivalent to 1 over 2. 15 over 20 is equivalent to 3 over 4. Right? You divide this by 5, you get 3. You divide this by 5, you get 4. These are equivalent rational expressions. So they'll come in handy if we want to add or subtract these rational expressions here. They can be determined by multiplying an original fraction, aka a rational expression, right? Sometimes called an algebraic fraction, by a fraction equivalent to 1. In other words, multiply the numerator and the denominator by the same value. And again, that's exactly what we did up here, right? Multiply the numerator and the denominator both by 4. Okay, determine two different rational expressions that are equivalent to each of the following. So I could take this and just multiply by, let's say 3 over 3. And when I do that, remember, up here, there's two terms, right? So really consider them in brackets, and you've got 3. So it would look like this. I'll go 3 times 4x squared plus 8x over 3 times 4x. So remember, distributive law. So this will be 12x squared plus 24x. And in the denominator, 12x. Now this is not in simplest form, right? As a matter of fact, that's the next lesson, is really just getting simplest form. This is getting an equivalent rational expression. So it would be as if we had to take this and add it to something that had a denominator of 12x, right? Then we would have to make this have a denominator of 12x to get an equivalent rational expression. Let's do one more. We'll just do one a little more complicated. Let's say I take 4x squared plus 8x, and I multiply that by 2x minus 1. Now, in order to be equivalent, I have to multiply by a fraction, right, equivalent to 1. So this is equivalent to 1, right? Same thing, top and bottom. Okay, so the top is going to have to be expanded using FOIL. So we get 8x cubed minus 4x squared plus 16x squared minus 8x. Okay, so FOIL it out. We've got first 8x cubed minus 4x squared plus 16x squared minus 8x over, so 4x times 2x is 8x squared minus 4x. Okay, so distributive law. Multiply this, then this. Now this actually collects, so we can simplify it. 8x cubed plus 12x squared, right? So minus 4 plus 16 is plus 12. X squared minus 8x over 8x squared minus 4x. So this is a more complicated expression than this was, right? We're not simplifying this. Again, in the lesson after this, we will do some simplifying. We're just saying, I want to get an equivalent rational expression. So you got to say, I need to multiply by a fraction that's equivalent to 1. 3 over 3 is 1. 2x minus 1 over 2x minus 1 is 1. Okay, let's do this guy here. And you know what, let's multiply by 5x. Okay, if I do that to the numerator, I do that to the denominator. Whoa, got fuzzy. These are binomials. Best thing to do with binomials is put parentheses around them to remind you that this multiplies both of these terms. So 3 times 5x is 15x. Oops, 15x minus 25x squared over 20x plus 5x squared. Okay, so that is an equivalent rational expression, right? They're the same. In other words, if you put a value for x in here and worked it out, and then you put that same value of x in here, they would evaluate to the same number. Okay, that's something you can try if you want. Take my word. Okay, it'll work. And let's do one more, right? Because it says 2 different. So 3 minus 5x over 4 plus x. And usually when I see 2 terms, I like to always just put them in parentheses. And what are we going to do? Let's pick a term. We'll do a binomial. How about something simple? Well, just with some numbers. How about 3x minus 2? Now, if I put that in the numerator, then I need the same thing in the denominator, because this expression has to be equal to 1, right? Same thing top and bottom. Otherwise, they will no longer be equivalent. Okay, so I'm going to FOIL both of these, right? We'll get 9x, that's the first, minus 6, minus 15x squared, plus 10x. We are now at the, how small can you write? So 12x, again using FOIL first, minus 8, plus 3x squared, minus 2x. And if we collect like terms, separate that out. So I'm going to lead with the x squared term. We always lead with the term of highest degree. Minus 15x squared. I've got 9x plus 10x. That'll be plus 19x minus 6. That's the constant. And then here, again, we want to lead with the x squared term. So that'll be 3x squared. 12x minus 2x. That'll be plus 10x. Watch your signs. Minus 8. So again, this and this are equivalent rational expressions. Okay. If you graph them, now we're not going to do any graphing of rational expressions, but if you graph them, you would see the same graph if you put a value for x in. Like, let's say here, if I made x 0, then this would disappear in this. We would just be left with 3 over 4. If I make x 0 here, that's gone, that's gone, that's gone, that's gone. I've got negative 6 over negative 8, which is positive 3 over 4. So they'll be equivalent rational expressions. Unless, all right, and here comes the unless. What if x is negative 4 and I put that into this expression? We're going to have a problem. Okay, because 4 plus negative 4 is 0. Up top, negative 4, that'll give me positive 20. I'll have 23, but I'll have 23 over 0, and I'm not allowed to divide by 0. So what does that mean? Well, that leads to something called a non-permissible value. It is the value of a variable that makes the denominator, right, the bottom, the denominator of a rational expression equal to 0, right? Remember, we cannot divide by 0. Non-permissible values, right, NPVs, are determined, you can work them out, from the rational expression after the denominator has been factored. Okay, so you're going to find out that from this point forward, your first step in doing anything with a rational expression is to factor the denominator. Okay, so I hope you got some good factoring practice on the last lesson. So after it has been factored, but before it has been simplified. Okay, and we'll run through these steps each time. We'll do a bunch of examples. When you do the work, just run through the steps each time, right? They're always telling you what to do and how to do it. Okay, so determine the non-permissible values and state the restrictions. Now these two things, a non-permissible value and a restriction, are very closely related. And 99.9% of the time, we are actually going to do restrictions. So even if we ask for, and here's the deal, if we ask for a non-permissible value and you give the restriction, it's fine, we'll give you the marks. If we ask for restriction and you give the non-permissible value, that's fine, we'll give you the marks. But I can tell you, anytime I've seen anything on the diploma, it's always asking for the restrictions. Okay, so when we do rational expressions, you're always going to be looking for restrictions. All right, here's the deal. So all we're doing is determining the non-permissible values. So here it is. To get the non-permissible value, set the denominator equal to 0 and figure out what value of the variable would make this 0. What makes this expression 0? You don't have to show the work. You could just say, hey, if I put a 3 in there, 3 minus 3 is going to be equal to 0. So that is the non-permissible value. And wait for it. Here's the restriction. So for the non-permissible value, we say what x is. We say x equals 3. That's the non-permissible value, right? That is the value that is not permitted, non-permissible, not permitted. X equals 3 is not permitted. The restriction is what can't x be? And so what we do is just take the non-permissible value but write it with a not equals. So this is the restriction. The restriction is just saying x cannot equal. Okay, and you'll see questions on the diploma, and they're going to list restrictions. Okay? All right, so let's look at this one at a time. So we want to factor the denominator. Okay, this is already in a factored form, right? It's already split out. Factor means to write it as a product. So what we're going to say here is, we're going to say, well, there's two values, right? There are two values of x that would make this 0 when you have x times x plus 5. So you can do it this way. You say, all right, look, I've got x times x plus 5. I want that to be equal to 0. Well, that will happen if x is equal to 0, right? You make x 0, it's going to be 0 times, and in this case, it'll be 5. But it doesn't matter. 0 times anything is 0. Or you can make x plus 5 equal to 0. And to do that, you make x equal to negative 5. So the non-permissible values would be x equals 0, x equals negative 5. As a restriction, you say x cannot equal. It cannot be. And a lot of times it's easiest just to start with the lowest and work your way up. So we'll go negative 5, comma 0, right? We're saying x cannot equal negative 5 or 0 in this particular one. Nothing wrong with a negative 5 in the numerator. Negative 5 plus 4 is negative 1. Nothing wrong with a 0 in the numerator. 0 plus 4 is 4, right? It's only the denominator, right? Because we cannot divide by 0. So it's only the denominator. Okay, this guy here, we actually have to factor. Okay, so we look at this. Two terms with the minus sign. You might think difference of squares, but you got to think, no, wait. The very first thing I do in factoring is to see if there's a common factor, which in this case is an x. So we write x minus 6. Now this one we're just going to do by inspection, right? And we're just going to say x cannot be 0 and x cannot be 6. So you don't have to show any work when you're doing, well, I mean, here you should, right? You do really should show the, hey, look, I factored this, and now from the factored form. But you don't necessarily need to do this work, right? X plus 5 is 0, x is negative 5. You can just look at this and say, you put a 6 in there, you're going to get a 0. So x, and then, you know, instead of doing the non-permissible values, we'll just go straight to restrictions. All right, we look down here, x plus 4, and we just say x cannot equal negative 4, right? No work required. You didn't have to factor that. This one, you do have to factor. So we factor out a negative. So watch the sign, okay? So negative 5 times x gives me minus 5x. Negative 5 times positive 4 gives me negative 20. So even if we're just doing a common factor, you still want to always, well, in this case, not FOIL, use distributive law to multiply this back out. Negative 5x minus 20, okay? And really, we should say this. Negative 10x plus 5. Over, right? And at this point, we don't need to factor this, okay, over this, and then just say, well, x, okay, by inspection, x cannot be negative 4, right? If x is negative 4, this turns into 0. Negative 5 times 0 is 0, and you've got a number divided by 0, not allowed. This guy here, so I'll try not to, I kind of messed this up. I didn't put the numerator down. Okay, so what goes into 10 and 2 is 2. The biggest value, p, that goes into both will be p cubed. To get 2p to the 4th, I just need a p there. To get a 10, I need a 5 there. To get the p cubed, that's all I need, is that. Again, from inspection, I was going to put a little comma there. So p can't be 0. If you ever have the variable by itself, so by itself, like here, by itself, like here, by itself. Even if it's cubed, right, then you just say the variable cannot equal, well, it can't be 0, and here it can't be negative 5. So I'm going to go negative 5, comma, 0. Don't put parentheses around this. It's not a point. It's just a list of two numbers. And if you wrote p cannot be 0, comma, negative 5, that's fine as well. Okay, it doesn't really matter if they're in order. It's just sometimes if there's a lot of them, it's nice to put them in order. Okay, let's keep going. So in this case, all we're doing, so what is this? It's just a common factor. This isn't equal to anything, right? This isn't like, oh, this is equal to 5, so I can solve for x. We can't get a value for x here, right? This is just an expression. We can simplify expressions, we can change, we can get equivalent, right? I mean, that's what we're doing this year, right? Equivalent rational expressions. That's the point of this lesson. Okay, so from here, x cannot equal 0 and 7/3. Now you might kind of say, wait a minute, that happened pretty fast. How did you do that? So I'm going to show you. So first of all, we can actually just do the solution, right? You just say, all right, I need 3x minus 7 equal to 0. That would get you the non-permissible value. So 3x is equal to 7. So you see what I've done is by moving the negative 7 over, I've changed its sign. That's where this positive 7 comes from. I look at that and say, change the sign, put down positive 7. And then I'm going to divide both sides by 3. So 7 over 3. So I look at something like this. I just say, change the sign, go positive 7, divide it by this number. You get 7 over 3. Okay, so when you're doing restrictions, I don't really care if you show work. I'm just interested in the final thing. Do you have all of the restrictions? Are they all correct? Are you missing one? Are you missing one and your other one is incorrect, right? I mean, so your mark is based on basically that you have all of them and that they're correct. You don't have any additional ones, right? Like you're not saying x can't be 2 or something like that, right? This guy here, so x squared plus 4. All right, so is there a greatest common factor? Nope, there's nothing that goes into x squared and 4. Is this a difference of squares? No, that's a plus sign, not a minus sign. So there's nothing you can do with x squared plus 4. You can't factor it. As a matter of fact, when you square a number, the smallest value you can get out of that is 0. So to make x squared plus 4 equal to 0, then x squared would have to equal negative 4. Right? But you can't square a number and get a negative, right? So what you could just say here is there are no restrictions. All right, this guy here. So again, we're leaving numerators alone. Okay, two terms. So let's start with greatest common factor. 3 goes into 3 and 12, so we divide out the 3. And then we're going to say, wait a second, x squared minus 4, that's a difference of squares, so it can be factored as x plus 2, x minus 2. So my restrictions are x cannot be, well, 3 doesn't affect anything. So x plus 2, that means x cannot be negative 2. X minus 2, that means that x cannot be positive 2. And sometimes you may see this written like this, cannot be plus or minus 2. So you can write them individually, negative 2 comma 2, or you can just say plus or minus 2. Of the following rational expressions, let me clean this up a bit. Clean that up. Identify the equivalent rational expressions. Explain why they are equivalent. So this implies that either this is equivalent, is the same as this, or this is the same as this, or this is the same as this. We don't know which. But let's just try it out. So one way to look at this is I might look at this and say, how can I make 81c squared into 243c squared? I say, you know what? You could multiply by 3. Right? 81 times 3 gives me 243. If I multiply this by 3, I'm going to get 27c. So these two guys are not equivalent. Okay, so then, again, how can we check? So we know these two aren't the same. How do I get 81c squared to be 729? So you can just take your calculator, right? And you can say, what's 729 divided by 81? Okay, and that comes out as 9. So you'd say, all right, if I multiply that by 9, the number will be 729, and I'm going to need a c, 9c, right? Because I got to get a c cubed here. Okay, so what if I multiply this by 9c? I'll get 81c squared minus 81c. Oh, well, that's what that is, right? So these two guys are equivalent. So the first and the third. So this and this, they are equivalent rational expressions. Equivalent rational expressions. Since this isn't the same as this, and this is the same as this, then this cannot be equivalent to either one of those, right? So we don't even need to check that. Okay, applications. Where might we use these rational expressions? So let's take a look. Josephine is an accomplished long-distance runner on her school track team, back in the days when they had track teams. She has completed 3 kilometers of a 10-kilometer race, and it took her 15 minutes. She wants to finish the race with an average speed of 0.25 kilometers per minute. So when I look at stuff like 0.25, I just think, hey, that's 1/4, right? So 1/4 of a kilometer per minute. Determine the time in minutes that Josephine must run the remaining 7 kilometers. Okay, so let the time needed for Josephine to finish the race be, well, it's time. Let's call it t. Her average speed for the race. So average speed, will be the total distance. Speed is distance over time. The total distance divided by the total time. So you think about it, you drive to Edmonton, you're going to drive total distance of 300 kilometers and a total time of 3 hours. 300 divided by 3 gives you 100. On the top you've got kilometers, on the bottom you've got hours, right? So you'd have 100 kilometers per hour. So if you're trying to think about distance and time and speed, just think about driving to Edmonton. So her average speed is the total distance. Okay, so the total distance is, all right, so what's average speed? She wants to finish the race with an average speed. Okay, wait, so we know that. We can fill that in. So let's do that. So average speed. Okay, what information do we have? So we've got kilometers and we've got minutes, right? So I could use 0.25, but I'm going to go with that 1/4. 1/4. The total distance that she's going to go is 10. 10-kilometer race. And the total time, okay, that's what we need to know, the total time. Now when we get the total time from that, we will subtract the 15 minutes that she's already run, in order to figure out the remaining time, right? Determine the time in minutes that must be run, the remaining time. Okay, so we can kind of solve this. This is just like a cross multiply, right? So t times 1 is equal to 4 times 10. So t is 40. Okay, we don't need equal signs there. We don't need an equal sign there. So t is equal to 40. So the total time is 40. The equation needed to solve. All right, well, that's the equation needed to solve. So this is actually being done up here. The total time is 40. She's already run for 15, so the solution is that determine the time in minutes she must run. She must run the remaining 7 kilometers in, so let's just go over here. So total time is 40. Time spent, so the time for 3K is 15. So this will be the remaining time. So she must run the remaining 7 kilometers in 25 minutes, which means she finishes the whole thing in 40 minutes, and 10 kilometers over 40 minutes will be 1/4 of a kilometer per minute, right? 0.25 kilometers per minute. Okay, so that is equivalent rational expression. See here, this is an equivalent rational expression that we're using to solve a problem. All right, we'll see you in the next one. Well, not see you in the next one.